This is Cameroon GCE level chemistry 0715. Section A, Physical and General Chemistry. June 2022, Paper 2. Fellow learners, if you haven't subscribed for this channel, please take some time and subscribe so that subsequent videos will get directly to you. Thank you very much for taking your time to subscribe to this channel. Let's get started. We are starting with Section A. Section A. Section A states in Section A, that's Physical and General Chemistry. That is June 2022, Paper 2. Now is on 1A. Hydrogen peroxide decomposes according to the equation. The equation is given there. That is hydrogen 2 moles of hydrogen peroxide in aqueous solution decomposed to 2 moles of water and oxygen. The reaction is first order with respect to hydrogen peroxide and is catalyzed by manganese 4 oxide. Sketch in the space below the change in concentration. A change in concentration, that's the y-axis, of the hydrogen peroxide with time in the x-axis. Yeah, here, what you can do here is, now that you are in the laboratory, you are trying to see the decomposition of hydrogen peroxide catalyzed by manganese 4 oxide, and the concentration, you are not dealing with the concentration. You are dealing with the concentration of hydrogen peroxide. So now what happened is now here you want to see the rate of a reaction based on the concentration. By changing the concentration of hydrogen peroxide with time, how is the rate going to look like? Is it going to be a first order? Is it going to be a second order? Is it going to be a third order? But now that they have said that it's first order, this is how it's supposed to look like. Okay, let's go there. You sketch something like this. Okay. Okay, you sketch something like that. You can say this is that. You can say something like this. This is the time, and you can talk of the concentration here of hydrogen peroxide. The concentration of hydrogen peroxide, that is oxygen 2 here, and in mole per dm cube, you have to label it mole dm cube, and you have to talk of time here, in that time per second, per second. Now, you know that a first order reaction is something which is very sharp. The slope is sharp. Something like that. A first order reaction. The slope is really sharp. I can take you to this and you see what I mean. I've not drawn it to scale, but you can get it from this end here. This is how a first order reaction looks like. This is how a first order reaction looks like. The slope here is very sharp. The slope is really sharp. It's steep. A steep slope shows a first order reaction. That is how you are. So then you label your axis as mole per dm cube and time per second. And you show the arrows and how the reaction is in progress. And you also label the first order reaction. First order. So, and that is all. Thank you. Let's move to the second question. The second question is on, okay, 2. Define order of a reaction. What is the order of a reaction? For you to define the order of a reaction, you should know that the order of reaction with respect to a particular reactant is the power to which the concentration of the reactant is raised in the rate equation. Let me put it here. I say the order of reaction. Okay. The order of reaction. The order the order of reaction. The order of reaction with respect to a particular reactant. With respect to a particular reactant is the power to which the concentration of the reactant the concentration of the reactant is raised in the rate equation. In the rate equation. I said once more, the order of reaction with respect to a particular reactant is the power to which the concentration of the reactant is raised in the rate equation. Okay. Now, what is a catalyst? What is a catalyst? For example, let me say a catalyst is something that can speed up the rate of a chemical reaction. And you know that at the end of a reaction, the catalyst is not used up. So the catalyst does not take part in a chemical reaction. It only speeds up the rate of a reaction by providing an alternative pathway, that is by lowering the activation energy. So in this case, we can say a catalyst, we can say a catalyst, a substance that increases a substance that increases or speeds up. You can say speed up. You can say speeds up. That speeds up the rate of a reaction. The rate of a reaction, but remains chemically unchanged. Chemically unchanged. Chemically unchanged. Remain chemically unchanged at the end. Okay, we said a catalyst, a substance that increases or speed up the rate of a chemical reaction, but remains chemically unchanged at the end of the reaction. Okay, let's go to state two postulates of the collision theory. What is the collision theory? You should know now what should be the collision theory. The collision theory, there are two postulates of collision theory. The two postulates of the collision theory are, in order of a reaction to occur, you should know that in order for a reaction to occur successfully, one, they have said just two postulates. There are three of them, but they have asked you to state just two. So for a reaction, in order for a reaction to occur successfully, for a reaction to occur successfully, for a reaction to occur now, for a reaction to occur successfully, one, the first postulate one, the reacting particle must collide in the correct orientation. That's the most important thing. Reacting particles must collide in the correct orientation. The first thing like that is what you are supposed to say. The reacting particles must collide in the correct orientation. They must collide in the right orientation. That's the first thing. That is for the collision theory. For a reaction to occur successfully, the first postulate is that the reacting particle must collide in the correct orientation, or you can say must collide in the right orientation. Postulate number two. You can say particle must have adequate or what goes sufficient energy. Particles must have adequate or sufficient energy. To permit mutual penetration of the reacting species. To permit mutual penetration of the reacting species. Then the last one, the rate of a reaction is proportional to the rate of reacting collision. You can state that one. You can still state that one if you forget. The rate of a reaction is proportional to the rate of reacting collisions. The rate of a reaction. The rate of a reaction is proportional. The rate of a reaction is proportional to the rate of what? To the rate of reactant to the rate of reactant collisions. This postulate is that a reaction rate increases as concentration increases. That is the meaning of that rate of this postulate. So let me go back again to the postulates. For a reaction to occur successfully, the first postulate is that the reacting particle must collide in the correct or in the right orientation. Number 2, particle must have adequate or enough energy to permit mutual penetration of the reacting species. Number 3, the rate of a reaction is proportional to the rate of reactant collision. What there I mean, reaction rates increases as concentration increases. Okay, let's go to part C. What is Born-Haber cycle? What is Born-Haber cycle? By now you should know the Born-Haber cycle because you have been writing. You must have been doing it. You must have been doing a lot of calculation on it. So what is a Born-Haber cycle? A Born-Haber cycle, like the one you see below here, we can say this is a particular type of enthalpy cycle used to calculate the lattice energy. That is just all. The main aim here is just to look for lattice energy. So we can say, we can put it in this way. We can say this is a particular type. This is a particular type of enthalpy. A particular type of enthalpy cycle. A particular type of enthalpy cycle used to calculate the lattice energy. This is a particular type of enthalpy cycle. This is a particular type of enthalpy cycle used to calculate the lattice energy. That's just all. Let's move on to C1. C2. C2 is talking on. Below is the Born-Haber cycle for the formation of sodium chloride. That's the equation that is given there. And then we have been told label the energy changes represented by delta 1. That is energy change in enthalpy 1, change in energy 4, and in 6, delta 6, delta 1, delta 4, delta 6. Okay, looking at the diagram very well, you will see that. Look at the diagram very well. You will see that delta 1. We have been told to label delta 1. Delta 1 is delta 1. Where is this delta 1? This is the formation of this lattice. That is the formation of the crystals, sodium chloride. The formation of sodium chloride crystals. That's the formation of the sodium chloride crystals. Then if we go now to 4, 4 is 4 is preparing. That is, we are preparing sodium to undergo what we call the first ionization energy. In that case, the sodium becomes the gaseous state, because that occurs only in the gaseous state. Now at the gaseous state. So we go to 6. 6 is 6. Under 6, we have the lattice energy of sodium chloride. So let's put it briefly like that. 1 is say 1. 1 is 1 enthalpy change or formation of sodium chloride. Can put it like that. Enthalpy change. Enthalpy change of formation. Enthalpy change of formation enthalpy change of formation of sodium chloride. So the first one is enthalpy change of formation. Enthalpy change of formation of sodium chloride. Then the second one is delta 4. Delta 4 is first ionization energy of sodium. Is first, can say first ionization. First ionization energy. First ionization energy of sodium. First ionization energy of sodium. Now we can go to number delta 6. Delta 6 is talking on, as I said, is lattice energy of sodium chloride. So it is lattice energy of sodium chloride. So that is it. The first enthalpy of formation of sodium chloride, first ionization energy of sodium, and lattice energy of sodium chloride. So those are the enthalpy changes. So now we go to 3. 3 is explain in terms of enthalpy change why some arrows are pointing upward, and some arrows are pointing but downward. Okay, it's very as we said, it's very simple, and all the direction of the arrow, all of them, they have a meaning. So in that case, the enthalpy change the enthalpy change of arrows pointing upward indicates that the reaction is endothermic. If the arrow is pointing upward, it indicates that the reaction is endothermic. While the enthalpy change of arrows pointing downward shows that the reaction is exothermic. So that is what you are supposed to put there. Let's move on and see how we can do that. Okay. Um. I said that here. Mhm. Okay. Okay. Let me use this ink. Now, I said the enthalpy change is say explain in terms of enthalpy changes. Why? So enthalpy change of arrows pointing downward. Okay. Okay. The enthalpy change of I can put it this way. Okay. Enthalpy change of arrows pointing downward. Okay, let me put it in that form. Enthalpy change. Enthalpy change of enthalpy change of arrows of arrows pointing enthalpy change of arrows pointing upward indicates 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 of arrow enthalpy change of arrows pointing upward indicates enthalpy change of arrows pointing upward indicates that the reaction indicate that is the reaction is what? The reaction is endothermic. Endothermic, that is positive, has a positive value. It has a positive value. It's endothermic. While enthalpy change, while enthalpy change, while enthalpy change, while enthalpy change of arrows, while enthalpy change of arrows, excuse me, uh, of arrows pointing downward, shows that shows. Oh yeah, excuse me. Welcome back, please. I said while enthalpy change of arrows pointing downward, they show shows that the reaction is exothermic. That means the reaction that means the reaction has a negative value. Let's get back again. I said that because, as they said, in terms of enthalpy changes, now enthalpy change of arrows, the enthalpy change of arrows pointing downward indicate that the reaction is endothermic, while enthalpy change of arrows pointing downward shows that the reaction is exothermic. That is just all. Okay, the D part of it. Given that the X-ray power pattern of potassium chloride shows a cone with an angle that is theta, which is 13.98, and the distance between successful layer is 6.73 times 10 to the minus 3 cubic centimeters. That is the distance. Use the Bragg equation to calculate the wavelength of the X-ray. Yeah, this is diffraction. Involves diffraction and X-ray using the Bragg equation. However, the Bragg equation, this is the Bragg equation. Fellow learners, this is Bragg equation. Is n. Bragg equation is n lambda. That is the equation is m lambda, which equals to 2d 2d sine theta. 2d sine theta. Okay, 2d sine theta. Now 2d sine theta, which means that we have been asked to calculate the wavelength, and the wavelength is that's the wavelength we are talking of lambda. So the wavelength here, if we make the wavelength the subject here, the wavelength is going to be lambda. Is going to be lambda, which is equals to 2 into d all over n thing sine theta. Okay, theta now is what? Theta now is from the information from the data that will be given us here is 13. Oh God, is 13. 13 degrees 98 98. Yep. Now that is the value for it. Then the value for the distance is d is 6 I think 6.73 times 10 times 10 to the minus 9 cubic centimeters. Cubic centimeters. Now remember that n is the order of diffraction. Diffraction. So n, this is lambda, which is the wavelength, and the n is the order of diffraction. And the order of diffraction is in a consecutive way. It can be 1, it can be 2, it can be 3, it can be 4. The order of diffraction times lambda. So now substituting in our equation, we will have lambda there, which is equals to 2 into what was d? The distance was 6.73 times 10 to the minus 9 okay, cubic centimeters. cubic centimeters times sine 13.98, 13 degrees, yeah, 98 divided by 1. All this divided by 1. All this divided by 1. And if we do our calculation very well, we do our calculation very well. We are going to have our answer is going to be in terms of it's unfortunate I don't have a scientific calculator here with me to calculate sine for sine. So please, you can multiply 2 times 6.73 times 10 to the minus 9 cubic centimeters, and then times sine 13 degrees 0.98, and divide it by 1. You will have lambda, but your answer will be in terms of nanometer. Your answer will be in nanometer, please. John, I don't have science. I don't have a calculator, a scientific calculator to give that now. Nanometer. So just do the calculation, look for the sign, and multiply and divide by 1, and you have the answer there. Okay, let's move to E part. The E part of this is the E part of it. Covalent bonds, ionic bonds, and intermolecular forces are building forces in substances. Covalent bond, ionic bonds, and intermolecular forces are building forces in substances. Define what you understand by a covalent bond. What is a covalent bond? A covalent bond. A covalent bond, you know that a covalent bond is a bond that is formed by sharing of electrons, and that usually occur between nonmetals. Because they have a similar electronegativity. For that reason, you will have to define a covalent bond is, you can say a chemical bond. You can say this is a chemical bond formed by sharing of electrons between atoms, with all the atoms involved achieving a full outer shell of electrons, or achieving a full octet of electrons. You can put it in a way like that. Okay, let me just put it here. I said a covalent bond, a chemical bond formed, a chemical bond formed by the sharing of electrons. Sharing of electrons between atoms. Between atoms with all the atoms involved, with all the atoms involved achieving a full outer shell of electrons. Or you can say achieving an octet of an octet of electrons, achieving a full, or you can say achieving a full octet of electrons. Yes, a full octet of electron. Full octet. Achieving a full octet of electron. Full octet of electrons. So a chemical bond formed by the sharing of electrons, a chemical bond formed by the sharing of electrons between atoms with all the atoms involved, achieving a full outer shell of electrons, or achieving a full octet of electrons. Let's go to the second question is what? Ionic bond. Okay, what is an ionic bond? Ionic bond, now we have to do some work here. Ionic bond. Okay. Ionic bond. Remember, ionic bonds these are bonds that are formed between metals and non-metals. They are formed between metals and non-metals because of the wide difference in what? Electronegativity. The dipole moment is too wide. So because of this difference in electronegativity, a high difference with the non-metals having a higher one than the metals, they tend to pull electron. Or in other words, we say the metals tend to donate electrons to the non-metals. So we can now summarize a definition for ionic bond to be a chemical bond formed by the transfer of electron from one atom, usually a metal, to the other non-metal, resulting in electrostatic force of attraction between oppositely charged ions. Okay, let's put it this way. We can say a chemical bond formed by the transfer of electrons from one atom usually metal, to the other non-metal, to the other non-metal, resulting in electro resulting in electrostatic force of attraction. between oppositely charged ions. So we can now say a chemical bond formed by the transfer of electrons from one atom, usually a metal, to the other non-metal, resulting in electrostatic force of attraction between oppositely charged ions. That is what we call an ionic bond. Now, let's move on to the second part of it. The second part of it is dealing with intermolecular forces. Now, the second part of it is dealing with intermolecular forces. Now, here, you know what are intermolecular forces? Intermolecular forces, the van der Waals forces. There are different types of induced dipole attraction, London dispersion forces, or that is instantaneous forces of attraction. Those are what we call the intermolecular forces under the canopy of the van der Waals forces. Okay, identify the type of intermolecular forces in each of the following substances. Good. You don't need to disturb yourself. We have been given three substances, and we have ice. Ice, of course, in the solid. Ice is in the solid state. We have been given propanone, that is acetone or propan 2-one, and we have been given kerosene, that is a hydrocarbon. So now, let me give you the structures, and you will see and identify. From there, you will know how you can come out with the forces, the van der Waals forces. Look at these structures here. If you look at these structures here, this is the structure of ice. Ice, that is solid water. You know that water forms hydrogen bonds. And what is a hydrogen bond? A hydrogen bond is a bond. This is a chemical bond that is formed when a hydrogen that is covalently bonded to a highly electronegative element. These are words. Hydrogen covalently bonded to a highly electronegative element such as oxygen. The hydrogen now attaches itself to what? To a lone pair of electron on a second electronegative, a second highly electronegative element. So you see, these are hydrogen bonds because of what hydrogen bond what I've described. This is oxygen molecule has a double bond. On one of these double bonds, a lone pair of electrons. Sorry, not double bond. Sorry, please. This lone pair of electron on the oxygen atom. There are two lone pairs of electrons on the oxygen atom. This is just one. So one of it, because hydrogen is highly is attached to a highly electronegative element, and hydrogen is covalently bonded. Now hydrogen forms a bond, a hydrogen bond between these. A second one. Then this hydrogen from the second one again, because of the lone pair of electrons here, a lone pair of electrons on the highly electronegative element, oxygen. What happened? There is a hydrogen bond that is being formed here. But now, what is now coming there is there is some polarity. There is some polarity between the hydrogen and the hydrogen and the oxygen. Remember that hydrogen is highly electronegative, and the oxygen oxygen is highly electronegative, and oxygen, because of the difference in electronegativity, okay, this one is highly electronegative. It has a partial negative charge. It's highly electronegative. It has a partial negative charge. Because of this bond here, there is an induced type of intermolecular force, and for that reason, of this bond that is formed here and the cloud of electrons that are found here, there is an instantaneous type of a dipole that is allocated there. So now the one is has a partial is partially, excuse me, because of this, we it has a partially negative pole, and this one has a partial positive pole, and this, it continues like that as it is being bonded to, as hydrogen bonds are being formed in an ice molecule. So in this, we say this is a dipole because of the difference. There is a dipole because of the difference. So this one, because of the bond that's being, it induces a dipole here. A partial negative is attached here. The same way, because the one is positive, is negative, as it forms a bond here, as it forms a bond here, a partial negative is induced here. Because of the partial negative here, a partial positive is also induced here. So we call them here. There are two types of forces that are here. The type of forces involved in ice molecule is what? We say ice molecule is relatively weak dipole. We say they are dipole because hydrogen is not the difference in electronegativity, or the dipole moment is too high. So you see this one, there's a positive here and there's a negative here. So we call it dipole intermolecular forces. So there's dipole intermolecular forces. Because they are because they are between molecules. The molecule of water and the other molecule of water, the molecule of water, the molecule of water. So in other words, the hydrogen bonds that are being formed, we call them, these are what we call the dipole intermolecular forces. Hydrogen bonds are intermolecular forces. So let's go to ice. Ice, as stated there, is an intermolecular force. So ice, the type of force here is what? For ice, we say the intermolecular force there is relatively weak dipole intermolecular forces. Relatively weak dipole intermolecular forces. Secondly, I'm giving two because you can choose. Again, what we call London. This is one and this is two. London dispersion forces. London dispersion forces. London dispersion forces, LDF. The London dispersion forces. So that is another force that you can get there. Then you can go to propanone. Propanone. If you go through propanone, you are going to say we have a dipole here, and we have London dispersion forces. Let's go to propanone, and you will see what is there. For propanone here, you see the structure of propanone. This is the structure. Look at the structure of propanone. Propanone is acetone. Acetone is what we call propanone. Here, this is the structure of acetone. This is a polar. Carbon and oxygen. Carbon and oxygen, there is a difference in the electronegativity. For that reason, there is a dipole here. For that reason, there is a permanent dipole here because of carbon and oxygen. A permanent dipole of attraction. This is the two. Permanent dipole attraction. Then again, because this one too can also form intermolecular forces. This one too can also form intermolecular forces with this other one because of the high electronegativity. Now we call them what we call a dipole forces that are being formed here. So there are two types. We call the London dispersion forces that are there, and there are also London dispersion forces that are there, and there are also permanent dipole forces of attraction. So here in this structure, the same thing you can see here in the structure of here. You can see this propanone. The propanone here, because of the structure of this carbonyl group, the CO group, the carbonyl group, and there's a bond that is from this bond that is from here. It is instantaneous because of the presence of the strong electronegative element here. So for that reason, we call it London dispersion forces that are being formed there. So now the forces here are the forces are for propanone, the forces are permanent dipole forces of attraction. Okay, permanent dipole forces of attraction. Okay, so propanone is permanent dipole dipole forces of attraction. Forces of attraction. Hello, as we said, permanent dipole, for ice has relatively weak dipole intermolecular forces, and it also has London dispersion forces involved in it. For propanone, from the structure you saw there, propanone has permanent dipole forces of attraction, and it also has London dispersion forces. Then for kerosene, if you look at kerosene here, you look at kerosene very well, the structure of kerosene. You look at the structure of kerosene here very well. This is kerosene here. This is kerosene here. Kerosene is non-polar. There's all of them. There's no big difference in the dipole moment between carbon and hydrogen that are there. They are all hydrocarbons. Hydrocarbons are non-polar. So in that case, we can say, kerosene has only a London dispersion forces. Why do I say London dispersion? London dispersion forces are instantaneous forces that are induced. These are induced dipole forces. They can only be induced if the molecule is attached to is closer to a high dense to a region of electron cloud, high density of electron cloud, if the molecule is closer to a region of high electron density, then because of it, there will be the what we call the neighboring molecule will induce a dipole into the kerosene molecule. So in that case, that's why we say what can only go here is London dispersion forces. So that is it. And let's move on to F. F is, if you look at F, F is, we are dealing with concentration and the order of chemical reaction. So we are going to do some few calculations in the F. There are some few calculations that we are going to carry out here in F. And the calculations are, they are as follows. Okay, let's say for so the intermolecular forces, as I said I said the first we have, no, we are on F. We are on F. F. So F is for the reaction. Nitrogen monoxide plus hydrogen to give nitrogen and water. Now, when you are given a reaction like this one and you have been asked to calculate the order of reaction, given the concentration of the reactants, the concentration of the reactants that is nitrogen monoxide, hydrogen, and their rate of reaction, initial rates. So in order to calculate the order for one, you have to do what? What you will have to do is you will have to keep a one constant. Yeah. So in this case, let's say the concentration for NO has been given, concentration for H2 has been given, and their initial rate of reaction has also been given. Now deduce the order of reaction with respect to what? Nitrogen monoxide and this. So we are calculating the order of reaction for this and this one. And we write, and you can still use that to write your red equation. So now F1, let's say we want to calculate for, we want to calculate the order with respect to NO. And before we go to hydrogen, NO, order with NO, NO, order, the order with respect to NO. Okay. The order with respect to NO. How can we do that? Okay. Let's say we want to calculate for NO. We have to keep hydrogen constant. Okay, in this case, let me say NO here is, I want to take, where is hydrogen constant? Hydrogen constant is here on the third and the fourth experiment. Third and fourth experiment. We can still use it here on the second and the third, on the first and second experiment, while keeping 0.15 mole per dm cube constant. 0.1 mole, 0.15 mole per dm cube constant. We can use the first and the second experiment. Or we can use the third and the fourth experiment while keeping 0.30 mole per dm cube constant. Let's move ahead. Okay, keeping this constant. Let's say the experiment 3 and 4. Keeping it constant, what we are going to do is it will be 60. It will be 60. Let me say, keeping it constant. It will be for NO. It will be 60. Let me say 0.60 divided by 0.30, which will be equals to their corresponding rates. Initial rates are 1.12 times 10 to the minus 3. Okay, mole per dm cube. Just take it like that. Okay, divided by what? Divided by 2. 2.8 2.8 times 10 to the minus 4. That's good. It's minus 4. Okay, what do we do here? If we do this like this, okay, all this so 0. The decimal point can cancel, so we can go up to the level of 2. This will be 2. 2 is to what? If we divide 1.12 times 10 to the minus this, okay, just dividing this by this, dividing this by this is going to give us, dividing this by this is going to, of the same basis, we are minusing, so it will going to give us 0.4, 0.4 times 10. So it is 0.4 times 10 times 10. Okay, if we do this like that, okay, 0.4 times 10. If we multiply 1 decimal point times this, is going to give us what? Is 4. So it will be 2 to what? 2 to what? 2 to 4. Okay, which implies that 2 to 4, which implies that, okay, is 2 to 4. Now we have to bring everything into the same base, into the same base. Okay, let's say this number raised to a power a certain number n will give 4. Will give 4. But that 4 must be raised to a certain number. Let's bring everything to the same base. So it will be 2 to what? It will be 2 to 2. Okay, if it is 2 to 2, now because they have the same basis, we can now say n is equals to what? N is equals to 2. And if n is equals to 2, if n is equals to 2, therefore we can conclude that the order, we can say therefore the order with respect to NO is equals to what? Equals to second order. Is equals to 2. That is second order. Okay, now that is the order with respect to 2. But now they said NO. Now let's see if we have space here to calculate this other one. The order with respect to the order. Let's use another one here because there are 2 we are supposed to do. Okay, the order with respect to H2. Okay, the order with respect to H2, we don't know. Let's go the same thing we did here the other time. Okay, the same thing we did here is that we have to keep NO this time constant. If we want to keep NO this time constant, okay, NO constant will be, we are taking experiment number, NO constant, we are taking experiment number, we can take experiment 1 and 4, or we can take experiment 2, experiment 2 and 3. So if, we can take experiment 2 and 3. We can take experiment 2 and 3. So now, in doing that, 2 and 3, let's take experiment 2 and 3, which is this one. Let's take experiment 2 and 3. If we are taking experiment 2 and 3, so keeping NO constant, it will be 0.5. It will be what? 0.15 divided by 0.15 divided by 0.30. 0.30 equals to what? Equals to, what are the rates? 0.15, yeah, 5.6, 0.15, yep. Okay, yeah, 5.6 here. So we are doing this. No. Okay. The 15 divided by this one 30. Okay, 1.4 equals to 1.4. 1.4 times 10. 1.4 times 10 to the what? To the 10 to the minus 4 divided by what again? 2.8. 2.8 times 2.8 times 10 to the minus 4. Okay, so in that case, we are using but experiment. We are using, which experiment are we using? We are using we are we are using 1 and I think 1 and 4. We are using 1 and 4. So in that case, if we strike this off, this and that, this, we are going to have, what are we going to have here? We are going to have this means we are going to have everything just divided. We are going to have 0.5. This is 0.5. It's a 0.5 here to the power n, which is this is still a 0.52 because one cancel this. This is 40. Yep. This is half of this, so it will still be 0.5. 0.5 equals 0.5, and which is raised to the power 1. So if we do this, so n is equals to what? We can now say n is equals to 1. So the order with respect to order with respect to H2, order with respect to H2 is equals to first order, that is 1. The order is 1, that is first order. So now they are now telling us the overall order. Now let's use this information to now get what is the overall order. So the order with hydrogen is 1. The order is 1. The order with NO is 2. Therefore, the total of it is what? The overall order of the reaction is 1 plus 2, which is equals to what? 3. It's 3. Now let's go to question is 3. If we do that, then I think we are already done with that. Now, once more, fellow learners, for this, we have to do some work here. Let me make a recap to you for all this. So here, especially on the intermolecular forces, we have intermolecular forces here in the molecules. You have seen here once more. That is what is needed in the intermolecular forces. There are different types of intermolecular forces. Let me give you some for purpose of revision. There are different types of intermolecular forces. We have London dispersion forces. These are forces that are being induced. Now, there are also dipole forces. There are dipole forces. These are forces. Let me dipole forces. These are forces like in this case here. Then there are also hydrogen bonds. So basically, you have London dispersion forces, dipole forces, and hydrogen bonds as intermolecular forces. The non-polar molecules are the one. Non-polar molecules, they are the one that have London dispersion forces. Non-polar molecules, like in the case of kerosene, they are the one that have London dispersion forces. Why do I say they are the one? Because they are only induced. Because they are not polar, the London dispersion forces, which are instantaneous forces, they are just temporal. They are only induced into them. So non-polar molecules or compounds, they have London dispersion forces. Polar molecules too, on the other hand, they have dipole-dipole forces and also London dispersion forces. So polar molecules, they have two, the dipole-dipole forces and the London dispersion forces. Meanwhile, non-polar molecules have only London dispersion forces because it is being induced into them. Then compound with, let me say, hydrogen attached to, compound like hydrogen attached to a fluorine, hydrogen attached to oxygen, hydrogen attached to a nitrogen. With these ones, they undergo what we call hydrogen bonds. They also undergo what we call dipole-dipole forces. And they also undergo what we call London dispersion forces. Then again, for the purpose of revision, for a compound to be polar, the difference in the dipole, there must be a high difference in the dipole moment. Then the central atom has at least one lone pair of electrons. Then all atoms around the central atom are not the same. Because if they are the same, like in the case of methane, they will cancel each other. So in that case, for a compound to be polar, there must be a wide range in the dipole moment. That's the electronegativity. The central atom must have at least one lone pair of electrons, and all atoms around the central atom are not the same. Then again, please, for a compound to be non-polar, central atom has no lone pair of electrons. All atoms around central atoms are the same. I gave an example for you, like I gave an example of methane, which is CH4. All are the same, and the hydrogen will cancel each other, and that will be all, making them non-polar. So, good examples of non-polar molecules are things. Non-polar are things like carbon dioxide. The oxygen on the other side and the oxygen on the other side, they cancel each other. So they will only have a London dispersion forces that are induced. Then polar molecule like let me say sulfur tetrafluoride, SF4, sulfur tetrafluoride. They are polar because they will have they are polar. They are polar molecules. They have dipole-dipole forces as well as the London dispersion forces. If you go to hydrocarbons, like the one I just showed you, the one for hydrocarbons. If you go for hydrocarbons like the one for kerosene, hydrocarbons on the other hand, hydrocarbons they are non-polar. Hydrocarbons are non-polar. So what they will only have will be what? Will be London dispersion forces. Then neutral elements like argon, neon, like let me say the noble gases. The noble gases are non-polar. So what they will only have will be what? London dispersion forces. So that is just all I can give you for the purpose of revision. Thank you very much for this. Once more, for those of you who haven't subscribed to this channel, please make sure you subscribe to the channel so that in subsequent videos you will get them. I will be starting the next edition with question number 2 on paper 2. Thank you very much. Bye bye.